Hello, welcome back to Quantum Computation Simplified. I'm Kadresan. This is second part of my video on this subject, quantum computing for finance. If you have not seen my first video, I request you to go through that first before getting into this video. However, I tried to recap the important points what we discussed in the previous video. Okay, so in the previous video, we saw the applications of quantum computing for financial analysis, namely the options pricing, portfolio optimization, VAR, CVaR calculations, derivative pricing, credit risk analysis, etc. We also saw an important quantum algorithm called quantum amplitude estimation, which can be used as a subroutine for some of these applications. Basically, it estimates the probability of a desired outcome in a quantum state. So when we model it, whatever we are interested in, we'll try to improve the probability of that instant what we are interested in. And this method provides a quadratic speedup over classical Monte Carlo methods. For the previous example, you may think that uh, quantum computers perform like classical ones, but that is for smaller problem due to hardware limits. However, the software is already capable of handling large financial models, and it's poised to deliver major advantages as quantum hardware improves. And that's the reason we want to learn about the quantum computing for finance. So in this video, basically we'll focus on portfolio optimization, meaning how to pick up uh, the desired number of stocks from the available stocks. We also do what's the probability of return and things like that. Finally, we will end up seeing how to calculate VAR and CVAR. Okay. All right. So let's start with portfolio optimization. So what's objective for this video? I mean, not only portfolio optimization, we do something extra on that. So first we'll optimize stock selection. Then we estimate the probability of achieving a target return with the selected stocks. In addition to VAR, CVAR calculation for the losses, all using quantum tools, but we also do some baseline classical computing for some of these methods. So the scope of this video, we can say that how to make use of time series data from financial websites. We are going to consider 4 stocks, out of which we select 2 stocks through optimization techniques. 3 methods we are going to try it out: classical optimization, variational quantum eigensolver, quantum approximate optimization algorithm. So we have VQE, QA, OA. If you do not know about these algorithms, I again request you to go through my videos on these topics. Then after selecting it, as I told you, we want to see what is the return probability. Okay, we'll set the day's return. So I want so much. So what's the probability? Again, we'll use the QAE methods, which we got familiarized in the previous video. And finally, we do VAR and CVAR calculation. Okay, VAR, value at risk, conditional value at risk. The people who are in the financial field, they are familiar. But for the software guys, yes, as we go through our steps involved and the code, you will understand things better. While choosing the stock, we didn't consider macroeconomic indicators like GDP, inflation rate, interest rate, geopolitical risks, natural disasters or pandemics, and more importantly, company fundamentals. But then, what is that we are trying to optimize? So don't worry, we can handle. So what I'm trying to say is the way whatever you model in classical way, you can do the same thing in a better way. Quantum computer can handle all these factors better than classical computing. Why? We know the fundamental advantage of superposition. Suppose we are given n assets. Okay, let's say 100 assets. what is the best combination? So if I choose one or two or three, any two, any three, any four, like that, you have two to the power of 100 combinations when we have 100 assets to choose from. So that is very difficult process of calculation for classical computing, and it's very easy. So for 100 qubits, 100 assets, you just use 100 qubits. You'll be able to handle that problem. And problem will become very complex in classical computing when we want to introduce constraints, obviously, like budget, diversification, and sector caps. So some people may say, I'm interested only in companies dealing with the AI. Some people say, no, I'm not to that. I want to diversify my investment. So all those things, it becomes very difficult in classical computing, and it can be easily manageable in quantum computing. And with superposition, we can correlate the stocks, right? So which we saw it in the previous video. Okay, so now let's go deeper into portfolio optimization. Okay, so these are all the steps involved. First, we need to get the real data, right? Stock prices. I use the Yahoo Finance because it's freely available. So I'm going to use adjusted close price for each stock. We are going to consider four stocks, great stocks: Google, Apple, Amazon, and Nvidia. So if it's not available as adjusted close, so we'll use close stock. Every stock will come with different parameters like previous day close or today's open, today's high, low. Okay, close is the one what we are going to use. Or adjusted close, I think you know the difference, right? So if you consider in addition to close like dividend bonus issue, so that's what is called adjusted close. We need to compute daily returns, okay, from this time series data. So you take today's, if you want to calculate what is daily, today's return is previous data minus today's data divided by previous data, like that, right? And then you, after calculating daily return, you calculate the mean returns vector. Then you need to do one more interesting thing, covariance matrix. So particularly when you wanted to choose more than one stock, you need to develop this covariance matrix. Basically, it tries to give the relationship between the two stocks. Okay, you can choose whether the two stocks will offset the total value, or it will meaning cancel it, or it will amplify. So that is very, very important in order to look at the overall returns. Okay, then it's being an optimization problem, you need to maximize or minimize something, right? So here in this case, we are going to maximize expected return minus risk. Okay, and there's should be a constraint in general. So here our constraint is our money budget. Okay, so instead of saying how much money we wanted to invest, how many stocks you want to choose from. Okay, so that's what we are going to do. So with all that, we'll be building something called a quadratic program instant, and later we'll use this program instant for classical approach and two different quantum solvers. Okay, so typically our the maximization equation looks like this. Let's see what are the parameters or what are these variables. So x is basically it's a vector of binary variables, meaning if you are going to choose stock, it becomes 1, otherwise it's 0. So it's just a binary. This is the expected returns mu. It's very linear thing. Okay, but the portfolio risk is a quadratic term. Okay, I didn't expand this, but you can see it in any financial application or even in, I think, you may get it. And finally, this is important factor. This comes by experience. Okay, so the constraint is how many stocks you want to pick up, okay, based on money available with you. Good. Okay, so how to make use of these parameters? When we go through the code, you will be able to understand things better. But these are all the parameters or variables we need to build the quadratic program instant. Okay. After that, we are going to use that first in a classical optimizer that we can use it for baseline. Then VQE, QAOA. Both are basically having parameterized quantum circuits, and this is how you build the circuit. Of course, both will build the circuit in a different, I mean, in two different ways, and the circuits will have some parameters, which basically we will be changing it to get the desired result. Or okay. So once build the circuit, then you execute and finally make the measurement. You look at, you do some post processing and see the results. Is it as per expectation? If not, use some classical optimizer, okay, to change the parameters used in the circuit. So you come out with a new parameter, then you repeat the process many number of times till you get the expected result, or till you reach the number of maximum number of iterations. Okay. So if you do that, finally you will select two assets, or two assets will be selected by our code and given to us. So in this example, it has chosen Amazon and Nvidia, and we also get the objective value, the return minus risk value. So these are all the outputs. You can see first from classical optimization approach, then VQE, QAA. You can see here all have chosen Amazon and Nvidia. So this is the selection vector. The first two are Google and Apple. We didn't select, that's why it is 0. One thing which I'm surprised is the objective value is same for all. So I need to understand a little more on that. But otherwise, this is very easy to apply. Later, you will see the code. You don't have to really break your head much. Okay, after having chosen the two stocks, I want to know what's the return probability. So how do I define the return? So I'll set a value. Daily I should get 0.4%. So that is what I have set here. So again, I used the QA algorithm only, what we saw in detail in the previous video. In order to use that approach, you need to encode the return distribution using state preparation. So if you want to know about that, definitely you have to see my previous video. And there are different QA algorithms. In the last video also we use iterative amplitude estimation. It's a good one. Here also we are going to use. It's good for two reasons. One, it uses less number of qubits. The second one is it gives reasonably accurate answer. And then we compare with the classical method. So after doing this exercise, so what are the outputs? You get the QA estimated probability, classical probability, and visual statistical comparison. So this is what you get as an output. But here, since we consider only 5 days of data, it looks very simple. You don't need a computer to know the probability, because out of 5 days, we got 3 days, the return is more than the set value. So probability is 3 by 5, which is 0.6. So that's the number classical way of computing as given. But QAE is roughly 0.5885, close to 0.6. Okay. And definitely when we consider more number of stocks, it will not be that easy to know the probability, right? Again, the return, there's a lot of mathematics behind the returns. So all those things are explained in my previous video. You will see something in this video also when we go through the code. So afterwards, now what next? So the important part, VAR and CVAR. So typically people use this approach for credit analysis. Okay, so how a borrower behave, or I mean, based on borrower's behavior, how much we are going to lose or something like that. But in this case, we are using it in a different way. So VAR, the definition is, I need to first set a confidence level. So here I'm going to say I'm 95% confident that losses will not exceed a number. So that is the VAR. Okay. So when I say 95, there's a term I should use later when I build the model, that's called alpha. That is nothing but 1 minus 0.95, which is 0.05. So I hope it's clear, right? So given the day losses or the sample outputs, how confident you are. So, or I mean, you know the confidence level you have to define. So for that given confidence level, what is the expected loss? That is what you do. Okay. So for 95%, for the 5% which we are not confident, what is the expected loss? So that is given by conditional value at risk. Okay. These two parameters we are going to find out. So the steps involved are, again, you need to go back to Yahoo Finance, get the stock returns for the selected stocks. And an important parameter is being used as LGD, loss given defaults, which basically comes from credit analysis. How much you lose if a borrower defaults. So in this case, of course, we know there is no borrower, but we use the daily losses are treated as LGD. Then we need to build the quantitative risk model. Okay. So for that, there are a lot of parameters. The first one you are familiar now. Alpha is 0.05 for 95% confidence level. So this is an important parameter. It is basically, suppose I want to consider 5 stakes. Each day, what is the probability of getting my stocks in loss? So we just randomly generate, but in order to be more realistic, we need to look at the historical data to arrive at these numbers. Possibly a finance expert will be able to give. And this is another parameter called rho. So what does it say? It talks about the correlation between each day. For example, if a natural disaster happens, uh, it will affect for few more days, right? So that's then the number will be large. So 0.05 is like a weak link or weak relationship, we would say. The next point is very, very important. So though this probabilities for a stable market, I would say, it's not bearish or bullish, but in reality, anything can happen, right? So we're going to consider something like this. So the mean value is stable market. So this is bearish market and this is bullish market. Typically, we go up to, it's like a normal distribution. We go up to minus 3 sigma to plus 3 sigma. But we need to discretize, right? So again, to what levels? If you want a more accurate representation of the data, you need more qubits. Okay. But in this case, since we are using only 2 qubits, you get 4 values. So this is worst market and this is bad market. This may be good and best markets. Okay, so that will change the probability of getting into losses. So now, having defined all those parameters, you can build the model, and then from the model you can generate a quantum circuit. And interestingly, you don't have to do anything for you just call a function called Gaussian conditional independence. So using these values, it will build the quantum circuit. So that's very, very easy for us. You don't have to be neither a finance expert nor a quantum expert. All right. So afterwards, you execute the model, you get the sample output, right? So you collect all the samples and sort all the losses in ascending order, then you need to build something called cumulative distribution function. Okay, starting from zero loss, you keep on adding it until the maximum value should be 1. Once you have that CDF, then it becomes easy to estimate VAR and CVAR. Hope you got some idea on the application of quantum computing for portfolio optimization and VAR, CVR computation. Your understanding will improve once you look at the code. So I use the code available from Qiskit community at this GitHub uh, page. So, okay, so this is for portfolio optimization. So I used credit risk analysis and we modified it for portfolio optimization. Okay, so I made changes on both. Maybe I'll find a suitable location and share my code later. But otherwise, basically they are all drawn from these two GitHub pages. Okay, so now let's have a look at the code. Okay, I've already installed Yahoo Finance package. Okay, so I'm going to download the data from Yahoo Finance page. So first, there will be plenty of data, right? So I'm saying I'm interested in Google, Apple, Amazon, and Nvidia. And I'm saying that I want to look at the data of 1st March 2024 to end of March 2024. I'm going to download the data. And as I told you, I'm going to use just close data. If not, if that is not available, I'll use the closed data. So this is how the typical plot looks like, which we have seen it in the slides. So we're not doing much on this place. Now let's move on to optimization problem. So as you can see here, I'm trying to mostly use Qiskit of finance finance library or algorithm library. Okay. So same steps we need to follow. I just modified instead of 31 days data, I'll use only 10 days data. So same thing, we're trying to download the close data. And here we need to calculate the returns, daily return. Okay, so for that percentage change you calculate. Um, that is from for today or to yesterday and today you subtract and then divide by yesterday's data. So that's the percentage change. And for the first data, since we'll not have the previous day, we are saying drop not a number. So it's all Python statements. I didn't write or IBM didn't write any special code for that. I think some of you may be familiar. Then we need to calculate mu. Okay, again, we are using the make use of built-in functions, and we need to convert to NumPy format. Sigma, the covariance stuff, we need to calculate. This we do normally when you want to choose more than one stock. We need to say what is the risk factor when you do the optimization. Okay, then budget. This is the constraint what you are going to define. So now you make use of all the data and build an instant. We call it as QP. Okay. So first we'll use classical optimizer. Again, interestingly, it's all available within Qiskit. Okay, minimum optimizer. It's all given there. That's what we are doing it. Then we just solve it, and we are printing the output of this approach. So optimization result has chosen Amazon and Nvidia stock, and it has rejected Google and Apple. That's why you see here 0011. Okay, it is given the objective. Now let's use first sampling. First VQE, then QAOA. Okay, so I'm sure you would have seen my videos or some videos on optimization. We need to define the random seed value to assume the initial guess parameters. Then we need to say which optimizer I'm going to use. Quizzkit offers a couple of optimizers. Okay, so this one proven one, so I'm using Cobila. Then how many iterations I want to do, I'm just saying 250. Then you need to build the answers. Again, there are different circuits available, and within the high level circuit, you can define internally how you want to build. So all those things are defined here. Once, yeah, after that you need to initiate, I mean, you need to assign initial values. Then you build that instance sampling VQE, and that's what you are going to assign it. I mean, solve it. You are going to solve it through minimum eigen optimizer. So here you literally execute that one, and you get the result. Very easy. I'm not going into the detail because yeah, each one will take I mean, video to explain. So if you want to know more about these steps, please go through my previous videos. So this has also given the same result like classical approach. Now next we'll follow QA/OA approach. So we start with the random number for initial values. We need to choose a classical optimizer algorithm to get the new parameters. Need to set the maximum iteration. Then yeah, we are trying to create an instance for QA, assigning to a solver. Then we are going to solve it. So interestingly, I think yeah, you may be aware that you don't have to do the iteration, right? So the built-in function does it. So that's a very good feature of IBM Quizkit. You can see here it's a big optimization problem. If you want to build from the single gate or sorry, single qubit gate or two qubit gate, it's a very big exercise. You don't have to break your head. But if you want to learn more about that, certainly you can do it because the complete source code is available. You can really break the circuit and then see what's happening. You can try to optimize or improve certain part of the circuit. Okay, but here we are just following it. You can see a very, very simple way of doing quantum optimization. So here also we got same results like earlier K2 cases. The next one is having chosen Amazon and NVIDIA, we want to know what is the probability of getting a set return. So we are trying to calculate the mean returns like we did earlier. We are going to set the parameter called threshold, meaning I want to, what is the probability? I'm interested in what's the probability of me getting 0.4% daily return. That's what we are going to solve this problem. For that, you need to first define a label for the for the QA to work. So whenever there is a good return, I mean, or anything positive return, you say 1, otherwise you say 0. Okay. Then you need to normalize the data. Afterwards, yeah, when we build, depending on the number of qubits you use, you may have to pad it with zeros. So that is what is being done here. Then you have to prepare the circuit. You need to define what is good. So good is nothing but the label should be 1, meaning I get a positive return. Afterwards, you prepare the quantum circuit, and then you create an instant for estimation problem. Afterwards, okay, assign it to a QA algorithm and then run it. So I mean, it's very easy, right, to do quantum computing nowadays. So finally you get the result. I think this you have seen it earlier, right? So we set 0.4% somewhere here, return per day. So that's the line, and on 3 days we got more than that. Next, we'll jump into VAR QAR. It's little bit complex compared to the previous modules. So here again, you can see here we use mostly the finance library only. I start with the returns. So our aim is to see with respect to loss at 95% confident what would be my loss. Okay. So we are saying daily loss. See, all this time we were seeing returns. So loss is nothing but the negative of returns. And when you get uh, a good return, then this will become minus some number. It doesn't make a sense. We are going to limit it to 0 because we are interested in losses only. And we want to consider again for 5 days. Okay, alpha, we have seen all these parameters, right, earlier. So LGD is nothing but daily losses. Alpha, sorry, related to the confidence level with 95% confidence level means alpha will be 0.05. Then this is the correlation between the days, and finally how much Z we want to consider and how many qubits you want to consider for Z or Z. Okay. Afterwards, it becomes very simple. You can see here, just call this and call the circuit function to add the measurement. It's done. You are ready. The circuit is ready. See, this is a good aspect of IBM Qiskit for financial application. Then you just run it. You have to do some post processing. So that's what is done here. You have to get the samples, put it in ascending order, then try to build that CDF. First of all, before that, you need to convert to NumPy array values. That is what is being done. Then VAR calculation is very simple. Shorter loss, okay, where you get 1 minus alpha or 95% confidence. Okay, that is what is being done here. And finally, this is the result. So you get the red line here. Red line says that our VAR is 0.0319. That is at 95% confident that our losses will be lower than this. Okay. Okay. What about the remaining data? So the remaining data, the average value is 0.336, the tail probability. Okay. And this is where quantum computing is very useful, they say, particularly to handle CVaR values. Okay. Till now, we ran the code. We didn't see a single circuit. I'm sorry for that. I didn't go to the details because everything is ready to serve by IBM Qiskit. I'm sure even other service providers also will have similar functions. But still, no, as a quantum engineer, I want to know how the circuit will look like. Okay, I want to modify that. Then you can decompose and try to understand each of these circuits. Okay, I mean, I just give another reference. This circuit is meant for VAR, CVAR computation. All right. I hope you got some idea, and I think you need to practice a lot to become for better understanding or to become an expert. So let's go back to our slide. So these are all the references. I mean, the same thing, whatever I showed in the previous slide. I also given this list in my description column. You please go through that, understand, and you can see the difference of my code once I publish it in a GitHub location. I'll add it to the description. Okay. So keep trying. this code. I'll come back with more videos on quantum computing. Thanks for watching. Till then, bye bye.